Awesome. Well, I want to take the opportunity to thank the organizing committee for the opportunity to talk about precision radial velocities in the near infrared with the Habitable Swan Planet Finder. My name is Stefansson. I'm currently a NASA Sagan Fellow at Princeton University, and early next year I'll be moving to University of Amsterdam as a faculty member there. But I'm excited to talk to you about HPF, and let's dive right in. So what is HPF? HPF is a near-infrared spectrograph on the 10-meter Hubble Eberly telescope that we installed there in late 2017. A full on-sky science observation started in fall 2018. Here's a hit list of a few of the main parameters of HPF. HPF covers a wavelength range from 810 to 1280 nanometers at a resolution of about 55,000. We employ H2RG detector with 1.7 micron cutoff. And to enable precise radial velocities in the near infrared, we cool the instrument to 180 Kelvin. And our design philosophy was to maintain the temperature control there to 180 Kelvin with millikelvin temperature precision. One very important ingredient, this is what Suvad also touched upon, is to obtain precise radial velocities is your calibrator. With HPF, we have a state-of-the-art laser frequency comb, custom built by our close colleagues, Scott Diddams, Connor Frederick, and others at NIST and CU Boulder. I won't have time to go into the details of the HPF LFC, but the main point that I wanted to make here is that it covers the full wavelength range of HPF from 810 to 1280 nanometers, allowing us to obtain a phenomenal picket fence of nice lines that allows us to robustly and very precisely monitor the drift in HPF. The comb is working really, really well. It has an uptime in excess of 98%, which allows us to do robust drift monitoring as a function of time. So what I wanted to take a look at, let's take a look at what under the hood, what the drift of HPF actually looks like as revealed by the comb. So here I'm showing the HPF absolute radial velocity drifts from 2018 to pretty much today in two separate RV drift chunks. Let's take a look at the first one in black. The peak-to-peak variation is about 50 meters per second. There are a few bumps and wiggles over here that are due to observatory power failures over here, periodic pumping of liquid nitrogen fill and vent hoses that couple the instrument differently to the outside environment. And then we performed a scheduled thermal cycle where we broke vacuum to do servicing on the instrument, after which we're seeing some larger drifts than previously, but the comb allows us to very precisely monitor these drifts. I also want to highlight, I guess, the band here that is sort of 10 meters per second in width, but this is a 24-hour cycling of the liquid nitrogen fill cycle that creates an effective sawtooth pattern, which we'll discuss in further detail during the near-infrared splinter session tomorrow. But how is HPF performing on sky after correcting for these drifts? Here's an example of the HPF RMS performance on the nearby bright M-dwarf Barnard star, showing 2 meters per second RMS precision maintained over 2 to 3 years. And the RV precision or the information content here is about 80 centimeters per second. As an example of a separate target as part of the HPF survey sample, here's another target showing an RMS of 1.6 meters per second maintained over 4 years. The precision on this one is also better. So a component of the increased RMS scatter over here is a combination of instrumental effects, but also stellar activity. With HPF, we also have an additional calibrator, the HPF Edelon, and using then and comparing detailed measurements of the HPF Edelon and comparing it to the LFC, Ryan Terrian led an effort published in a paper just a couple of years ago, demonstrating evidence for chromatic radial velocity drifts, showing here in the upper left plot, where different wavelength channels are drifting differently. And this was really enabled, I guess, by the precise drift measurements enabled by the comb. And like Surath also highlighted, Molly Crater has a very elegant solution to an explanation for these drifts, and definitely attend her talk tomorrow, where she shows that this is pretty much just due to relaxation in the outermost layers of the Edelon. I also want to take the opportunity to give a shout out to Sitian Yu's poster, who has been performing detailed drift measurements with the HPF Avalon. One very interesting aspect of doing precise radial velocities on the HET is due to the particular design of the telescope. It's a fixed altitude design, which has then clearer than pupil variations as we track an object on the sky. And Shubham Kanodia led a detailed effort to look for any sort of correlations with pupil coordinates of the telescope, demonstrating very effectively that the HPF fiber scrambling design is very efficient at removing any sensitivity to pupil variations. So do check out Shubham's poster number 54 on that. Then we're very excited to talk about some of the on-sky science that we have been doing with HPF since we went on sky in fall 2018. A lot of these efforts have been focused on detecting and characterizing non-transiting planets as part of the HPF survey. Also, a lot of effort has been going into detecting transiting planets, measuring masses, characterizing atmospheres and architectures, then also characterizing their host stars and looking at binary stars and brown dwarfs. I won't have time to go into all of these, but I just picked a few of them to give you a sneak peek and some of the highlights of what we've been up to with HPF. The first one that I wanted to highlight is the GEMS effort, which started for giant exoplanets around M-dwarf stars, which has the goal to detect and characterize additional giant planets orbiting M-dwarfs. This has been a particularly poorly studied sample of planets, just from the fact that not many have been known since before the launch of the TESS mission. Here I'm showing then in this diagram planet radius as a function of planet mass, highlighting M-dwarf giant planets with the colored dots. And before GEMS started, only 4 giant planets around M-dwarfs had precise mass measurements. And with GEMS, we've detected and characterized 12 additional giant planets, which has allowed us to start to ponder questions of how does this sample of planets, of these giant planets around M-dwarfs, compare their radii, their masses, their atmospheres to giant planets orbiting hotter stars. And this is an effort led by Shubham Kanodia, Caleb Kanyas, and Jessica Libby Roberts, some of which are here in the audience and many more as well, highlighted in some of the papers down in the lower right. And I invite you to definitely ask them as many questions here during the conference as you can. I also wanted to highlight Jack Lupin's paper and effort to take a detailed look at precise radial velocities of the M-dwarf star Barnard star, or GJ699. This is an RV standard that many near-infrared instruments and other optical instruments observe. The HPF RVs are shown here in the red dots at the end. Jack led an effort to take in detail look at the claimed planet candidate signal at 233 days. In so doing, it looks like most of the signal is largely contained within a relatively narrow window of time, highlighted here in the middle, the 1,000-day window over here. We then defined a before and after sample, and Jack led a detailed effort taking a look at different periodograms of radial velocities here at the top. S, H, and K index measurements in the blue, H alpha measurements, and then the window function. Long story short is that most of the signal of the candidate planet here highlighted with the green vertical line is largely contained within the middle region here, and not as robustly seen in the other time periods. And this is then also where we see some a corresponding peak in the calcium S, H, and K index. So our best explanation is that most likely that this signal is largely due to a combination of stellar activity and then time sampling. And then an independent effort by Etienne Artico and the Spiro team has come to the same conclusion, taking a look at Spiro data as well. I also wanted to highlight Ryan Terrian's work on taking a look at magnetic variations, leveraging the potassium-1 line at 1243.5 nanometers. This is a very interesting and magnetically sensitive line that's in the HPF bandpass. And it's particularly interesting because it is sensitive to magnetic variations, and it's also not completely plagued by tellurics in the near infrared. Here I'm showing what the line looks like in the solar photosphere, and it's completely split into then two lines over here in spectrum of a sunspot. We also start to see then this in spectra, HPS spectra of AD LEO. Ryan then led an effort to take a look at equivalent widths, full width of maxima, and correlating that with difference or line width variations, allowing us to actually gain insight into magnetic variations in T-Garden star, and then also Barnard star, allowing us to gain insight into rotational magnetic variations in slowly rotating M dwarfs. This is also a very promising indicator for more rapidly rotating stars. And one of the main reasons why we built HPF was to carry out a large-scale survey called the HPF survey to gain insight into the planet population around nearby mid to late M dwarfs. Here I'm showing an expected yield of the survey, which is currently ongoing, where we're surveying about 40 mid to late M dwarfs within 25 parsecs. The long story short is that the yield very much depends on the how much observing time you get, which has been a challenge to completely secure. But in this simulation, the expectation would be sort of a dozen planets at more than 5 sigma and about a double of that at 3 to 5 sigma. And these will be very exciting candidates for direct imaging observations in the future. And in the very last couple of slides, I'm excited to mention that we're starting to detect some really exciting candidates as part of the HPF survey. I ask you to kindly not tweet this result because this is currently under embargo. And I'm getting very short on time over here, so I'll just wrap up. Where we have started to detect then a signature of a Neptune-sized planet around an ultra-cool star called LHS 3154b. And this is the first Neptune known to orbit in a short period orbit around an ultra-cool star. The host star mass is only 11% of the mass of the sun. And this is where LHS 3154b lands compared to other M-dwarf systems. And just give a shout out to Megan DeLamer's poster on occurrence rate analyses in the HPF TTO. And I'm also happy to talk offline in a dedicated poster, number 41, more on this system. With that, I'll conclude. I'll be happy to take any questions.
One question.
The question was, how are you calculating the LFC RV drift? So we have a drift model, and we're going to go into that in further detail in one of the splinter sessions. But we effectively have a template that we generate off the LFC, and then we then do shift the template around to have a 3-parameterized model that accounts for a linear shift, and then some additional higher order parameters. But that's how we sort of scan and look for the RV drift.
Thank you.
Mm-hmm.